Today, I'm going to talk about a new algorithm to alleviate the double sampling problem in model-free reinforcement learning. It's a joint work with Zach and Lexing from Stanford. So first, I will introduce what is the double sampling problem. Reinforcement learning is really about Markov decision process. And there are four important elements in MDP. First is state space. Here we assume the state space is a compact set in the Euclidean space. And second is action space. For example, we assume we start from S0 and we take action A0. Then we will arrive at a state S1 and obtain a reward R1. The state S1 is determined by a transition matrix, which gives you the probability distribution on the next state, given the current state and current action. And the immediate reward R depending on the state and action. And the policy pi is a map from S to the probability distribution on the action space. So pi S specifies the probability of taking action A at state S. And given the policy, MDP generates a trajectory, including state, action, and reward at time t. So we're interested in the state action value function Q pi. Q pi is the expected discounted cumulative reward starting from state S with action A. And this discount factor gamma is a constant between 0 to 1. And this expectation is taken over all possible trajectory under the policy pi. And we call this expectation as Q pi. And the goal of RL is to find the best policy that maximizes the return Q pi. And we call this maximum Q star as the optimal value function. And this Q star is also the fixed point of the optimal Bellman operator, T star. T star is defined as follows. It is equal to the expectation of the reward, here we call it capital R, plus gamma times a conditional expectation. So this expectation is on the next state and conditioning on the current state and current action. And we also take maximum of Q over all actions. There is a nice property about the optimal Bellman operator T star. That is the contractive property. So based on this property, we can use iterative method to find the Q star. And some commonly used methods in RL, such as Q-learning, DQN, are all based on this contractive property of the Bellman operator. However, there is some disadvantage about this iterative method. First, when the state space is large, the Q will be a high dimensional vector, then the computational cost will be large. Second, when discount factor gamma is close to 1, the convergence rate will be slow. So we can also, another method, we can also do function approximation for the value function Q. We parameterize the Q by a parameter theta. Unfortunately, under the function approximation, we no longer have the contractive property. So instead of using iterative method, we can transfer this fixed point problem to an optimization problem. Basically, solve the minimization problem so that the Q is the fixed point of the T star. And since the expressive of the nonlinear function approximation, we can always find a good approximate for the value function. For continuous state space or large state space, instead of representing the Q by a high dimensional vector, the function approximation can save us a lot of computational cost. Besides, this optimization problem can be more stable than iterative methods. However, this formulation has this so-called double sampling problem. I will explain why in this slide. So first, we want to solve this minimization problem. However, we only have a trajectory generated from this underlying transition dynamics. Here we assume the transition dynamics is a discretized SDE with a drift term alpha depending on the state and action. However, in model-free RL, this drift term is unknown. We don't have an explicit form of the transition dynamics. We're only given a trajectory that is generated from this dynamics. So when we want to solve this optimization problem by gradient descent, by calculating the gradient of the objective function, we have the red part and the blue part. The red is the Bellman residual. The blue part is gradient of the Bellman residual. And if we expand this optimal Bellman operator T star, we will have two independent expectations on the next state. Accordingly, for the unbiased gradient, we will also require two independent samples for the next state. And we can have the first sample easily from the trajectory. However, the second sample is usually unavailable in model-free RL. For example, we are in a continuous state space. It's usually hard for the dynamics to go back exactly to the same point and then do a simulation again. So that's why the second independent sample for the next state is usually unavailable from the trajectory. This is the motivation of why we want to propose this new method, which is called borrowing from the future. What we do is we move one step forward to ST plus 2. And this two steps can be easily obtained from the trajectory. And then we borrow the future step to the current state and approximate the second sample by the current state plus the future step. So imagine that when the drift term is smooth, then these two alpha, the value of these two alpha will be close to each other. Then we will have a good approximation for the second sampling of the next state. This is how this algorithm works. We update our parameter theta based on the unbiased gradient. However, as we said, the second independent sampling for the next state is unavailable. Instead, what we do for BFF algorithm is approximate this term by ST plus the future step. We can also generate this BFF to a more general version to borrow multiple future steps. For example, we can move two steps forward and then borrow this two steps to the current step and then average these two terms to get this 2BNN. And we can always generate to borrow n future steps. We also give a theoretical guarantee for our algorithm. We assume the underlying dynamics is a discretized SDE where the drift term alpha depending on the state and action. The most important assumption is this one. We assume the underlying dynamics change slowly with respect to actions. Basically, we assume the alpha, the total variation of alpha on the action space is upper bounded by a constant C. Under this assumption, we can prove that the difference of the probability density function of BFF and unbiased SGD is exponentially decay and eventually stabilize at an error of order epsilon times this term. This term is the smallest Bellman residual that the unbiased SGD can achieve. And we also verify our theory and algorithm by some numerical experiments. We first test our algorithm on this continuous state space where the underlying dynamics is a discretized SDE. Here we assume action is +1 or -1. And time step epsilon is 2 pi over 32, and noise is 0.2. And we approximate the value function by a 3-layer neural network. And the uncorrelated sampling is basically the unbiased SGD, which is unrealistic for model free RL. Here we just use it for a reference solution. And we compare our BFF with sample cloning, which we just duplicate the first sample to the second sample. This will be worse than our method because these two samples is correlated with each other. But our method will reduce the dependence of these two samples. And also another method is called primer dual, where they transfer this minimization problem to a minimax problem so that they can avoid two sampling in this formulation. However, we will see in the numerical experiments that when this maximum is taken over non-concave functions, then it will become unstable. So here's the result. We can see the green one is the unbiased SGD, and two versions of our method, 1 BFF and 3 BFF, are both very close to the unbiased SGD. And the sample cloning method has a much larger error compared to our method. And the primal dual method converges much slower than our method. And we also show here in this picture about instability of the primal dual method. We do 10 simulations of this primal dual method. You can see the arrow, the convergence of the arrow is quite different among these 10 simulations. And we pick the best one. And the convergence rate is still slower than ours. We also test our method on the cut-pull example from OpenAI Gym. And since the underlying dynamics for this example is actually deterministic, so we put some noise into the dynamics. We can see that our method, the y-axis is the value function. So we can see our method increase the value function fastest. And the 1 BFF compared with the 2 PFF is a little bit slower, but still perform pretty good. And the sample cloning method converge to the maximum value function much slower than our method. And the primal dual method don't even converge. So here is a summary. First, we propose a new algorithm to alleviate double sampling problem in the model-free control. Second, we can see that this method outperforms other methods, especially in the case where the state space is continuous and underlying dynamics is smooth. Third, we also give this algorithm some theoretical guarantees. So this is all for my talk. Thank you.